3-dimensional volume. Similarly, one can think of higher dimensional volumes. So here, when we say relativistic point particle, it is understood that we are talking about a 0-dimensional object. Now we want to generalize these ideas to 1-dimensional objects. Okay, we want to generalize these ideas to 1-dimensional objects, and so we would need one extra coordinate to describe 1-dimensional objects. And so, or where alpha is 0 or 1. So, I could write the same coordinate x mu that I used earlier, but now with one extra coordinate. It's a function of not only tau. For relativistic point particle, x mu was a function of tau, but now it's a function of tau and sigma both. Okay, tau and sigma both. I could call tau as sigma 0 and sigma as sigma 1. Okay, and I could club these two together to call it sigma alpha. So sigma alpha is a alpha vector, in the bird-seed space. Sigma alpha is a alpha vector in the bird-seed space. What about x mu? X mu is a mu vector, but in the target space. Target space-time or the space-time manifold or the ambient space-time. So this is how we happen to have two kinds of spaces. Okay, that was the bird line space. Now the bird seat space. Okay, so if the 1-dimensional object moves like this, it creates a bird. It spans or shifts out a surface which is called as the. This was the bird line. And this is a bird seat. If I have a open string with two ends free, it is also parameterized by two coordinates sigma and tau. This is also parameterized by two coordinates sigma and tau. However, here sigma along the length makes a loop, so it's a closed. So this was a open string. This is a closed string. And as the closed string moves through the space-time, it would span also. This is also a bird seat, but it's a tube-like. Okay, and this is more of a seat-like. Okay, that's the only difference. So these are the two topological possibilities for considering the bird seat, and we can parameterize this bird seat by the two coordinates. These, of course, sigma 0 and sigma 1. You see, and this mu h we say is a mu vector in the target space. Now, if we like, we can define sigma plus minus as sigma 0 plus minus sigma 1. Okay. So instead of dealing with this is in the light from dynamics, many times light from dynamics has lots of advantages over the instant form. So when you have this sigma alpha with alpha equal to 0 and 1, you call it instant form of dynamics. Sigma alpha with alpha equal to plus and minus, you call it light from dynamics. Okay. And similarly, if you want to have x mu, it is your choice. If you need x0, x1, xi, I equal to 2, 3, up to d minus 1, let us say 25 for the bosonic case. And we will see when you consider the superstring action, then last time we had derived a limit that there was some normal ordering constant and the dimensions, so-called critical dimensions, they turned out to be d equal to 26 for the Bosonic string theory. And this time, by the same argument, by the same logic, by the same requirements, when we consider the mass spectrum of the overall theory, including the fermionic fields and the bosonic fields together, this d would then become 10 automatically. So otherwise you would not get consistent results. Okay. So the dimensions of the string theory would get reduced to 10. So there are several advantages there are several plus points. They appear to be complicated and difficult, but they are not. As I told you that in the superstring theory, you can live with just doing n equal to 2 supersymmetry. N equal to 1, capital N equal to 1 and capital N equal to 2 supersymmetry, which means number of the supersymmetry transformation parameters, epsilon, which we introduced, is 1 or 2. That's all. And not anymore. Okay. So here again, this is one thing, and this is the instant form, and in the right form you can write it as x plus, x minus, and x I. So here x plus minus you could define as I will tell you what happens if you take a factor of square root 2 here, and if you don't take it here, you can take it here also if you like. Okay, but one has to watch out in the two metrics have to be related properly. Okay, here if you don't have this factor, then a factor of 1/2 or 2 hangs around upstairs and downstairs. I will show you how. And if you take this square root of factor, what happens? In that case, you don't have that factor of 2 hanging around. So, but it's a conventionally what the people are doing. Let us follow the same. So for x mu, they follow this kind of thing prescription, whereas for sigma alpha, sigma plus and sigma minus, they follow it without square root of 2. But I will tell you how to handle this. Okay, so. What we have here is now that we have x mu sigma alpha or x mu, which is a function of tau and sigma. So this sigma is along the spatial length of the string. Okay, and it could be either open string or a closed string. That's all. So now a few important points before we go further. As we know from the differential calculus that you can express the area dA in some space defined by a metric, let us say G alpha beta, and we are talking about the world sheet space. We are talking about the world sheet space. So this is the invariant volume element, correct? Invariant volume element, so d2 sigma multiplied by square root of minus g. This is square root of minus gh we are considering a space defined by the metric G alpha beta. Okay, the worldsheet space. So you have G is the determinant G alpha beta, and you put it here. This is your invariant volume element. And this is your and d2 sigma, if you like, you can write as data. Okay, and therefore the action would be, now in the first case, for the relativistic point particle, the action was proportional to the length and was then minus mc times ds. Okay, here for the relativistic string, the action is then proportional to the area. So some string density, some constant, okay, some constant times dA, and this is equals to this, and if you like, you can integrate Ti to Tf and 0 to f. So you can, if you like, you can integrate from some initial time to some eigen time. And of course, whenever I am saying time, it's always eigen time, okay? Or even just a parameter. Originally, the tau and sigma are just two parameters, okay? But we can identify one of them as the eigen time. So this is then, as before, this is the famous Nambu-Goto action. So this is the Nambu-Goto action, and if you would consider here the